Okay, in this video, we're going to look at motion graphs and motion dot diagrams. So first of all, what is a motion graph? What is a motion dot diagram? Well, basically, both of them are used to visualize motion. So a motion graph, we have position versus time, velocity versus time, and acceleration versus time. And motion graphs are used for, after we collect data, they're used to visualize and determine different quantities. And we'll do this quite a bit in labs, and it's a very common practice to do on the AP exam. They'll give you a bunch of data, you'll have to graph that data and then determine some kind of quantity based on either the slope or area under the curve, something like that. And then a motion dot diagram, they're basically just diagrams that show an object's position over equal intervals of time. So it's basically like like a history of the object's motion. So I'll show you what I mean by that here in just a second. So motion dot diagrams, think about a car that leaks oil. The car, let's just assume, leaks 1 drop of oil every second. If the car is moving, the oil drops provide data about how the car is moving. So in the example shown, we have a truck. We can see that the oil drops are evenly spaced, and what that tells us about the motion of the truck is that it must have been moving at some constant velocity. So the truck is moving at constant velocity, which means acceleration is 0. So imagine you're moving down the highway, your oil is dripping once every second. If you're not speeding up or slowing down, the spacing between those dots is going to be equal distance. All right, so we're going to compare the motion of truck A with truck B. So try to determine the differences in how those objects were moving based on their oil drops. So if you look at this, it looks like the spacing between the oil drops for truck B, the spacing is larger than truck A, which means that truck B must have been moving faster, right? If they're both dripping once every second, in order to get a larger spacing, you have to move a little bit faster. So truck B is moving faster than truck A, but they're both moving at constant speed. All right, so now we have a couple of different situations, and we're going to try to determine the motion of each one. Starting with the first one, we've seen this one already. It's constant motion because the spacing between the oil drops are the same. So constant speed, acceleration is 0. All right, so take a minute, see if you can determine the motion of the second one. So notice how the spacing between the first and the second oil drop is smaller than the spacing of the oil drop, the second and the third oil drop. And then that's even smaller than the third and the fourth, and then that's smaller than the fourth and the fifth, and then so on. So what does that indicate about how that truck is moving? So it starts out at some speed pretty close to what the first truck was, but it must be speeding up. So in this case, it is accelerating. A is not 0. All right. Looking at the next one, it's a similar picture, but the spacing is increasing even more, increasing at a faster rate. So what we would say there is that it's accelerating, and we could say that it's accelerating more than the previous example. All right. And the next one, the spacing between the oil drops is decreasing over time. And so what that indicates is that the truck is slowing down. So you may have used the word decelerate, which means slowing down. In physics, anything that is speeding up or slowing down or changing directions or some combination of those, we say that it's accelerating. We don't really use the word decelerate, but decelerate does mean slow down. All right, and then in the final example, the truck is not moving. The oil drop is staying in the same spot. All right, so now we're going to move on to position versus time graphs, and then we'll kind of bring these together. So position versus time graphs are used to show the object's position over time. So a couple of things to make sure that you do when you make a position versus time graph. One is make sure that the position, that's X or Y, that's going to go on the vertical axis, and time is always on the horizontal axis. And then you always want to label each of your axes with a variable with units and appropriate increments. So here's an example of what that looks like. Okay, so when you take the AP test, they are going to want to look for, they're going to look for all of those things. If you forget to put your units, if you forget to put labels for each axis, if you don't increment it, there's no wrong. So there's many ways that you could set up the increment. If it doesn't make sense, they won't give you a point. So you have to keep all those things in mind. Usually graph problems are really easy to get a lot of points from AP questions. You just have to make sure that you're doing all of these things every time you're having to set up a graph. Okay. And then lastly here, the slope of a position versus time graph is the velocity. All right. So we'll look at why that is here in just a second. So here we have an example, and we want to graph the motion for the following motion dot diagram. And the spacing between each of those oil drops is 2 meters. So go ahead and take a minute, try to graph this, set up your Y axis, your X axis, and see if you can't get the graph to look like it should. All right, pause the video if you want to take time to do that, or I'm going to go over it right now. So here's what the graph looks like. We have position on the vertical axis. We have time on the horizontal axis. You could have just labeled the vertical axis as X since it's moving horizontally. So that would be the X direction. All right. And then this produces a linear graph moving at constant speed. So position is going to change at a constant rate with respect to time. All right, so we have our graph and we want to do a few things here. One is draw a line of best fit. So if you were doing a lab, for example, you would collect data, you would plot the data on a graph like this. It wouldn't be perfect like this. And you want to draw a line of best fit. It needs to be as close to as many points as possible. We'll look at a real life example when we have actual data to work with. In this case, it's a perfect linear relationship. So the line is going to fit on all of the points. So should look like that. All right. The next thing we want to do is we're going to pick 2 points on that line that you can use to calculate slope. So again, so when we do a lab or for AP questions, they typically don't want you to pick data points as your 2 points for finding the slope unless those 2 points, or unless one of those points is on the line. So you can pick at most 1 point. In this case, it doesn't matter. It's a perfect linear relationship. So I just picked those 2 points, and we're going to use those 2 points to calculate slope. So slope is equal to rise over run, or you can do y2 minus y1 over x2 minus x1. And if we do that in this example here, instead of delta y over delta x, we're actually dealing with position. So we could say delta x on the is the vertical axis. I know that's kind of confusing. You could say delta y, but since the truck is moving horizontally, I would have said delta x. So it's delta x over delta t, or x2 minus x1 over t2 minus t1, and that's going to be the velocity, right? So we've learned earlier that velocity is delta x over delta t, at least when we're dealing with average velocity. And you should get a value of 2 meters per second. So in this case, the average velocity is the instantaneous velocity, but we'll look at some examples here soon where that's not the case. All right, so now we have another scenario. We want to graph the position versus time for the following motion dot diagram. So take a minute and try to draw that, or you can follow along with me. All right, so this is what the graph should look like. The position of the truck is not moving. So it's at 10 meter at time 0, and it's just going to stay there. So this is just a flat line. If you were to take the slope of that line, you would get a slope of 0, which means velocity is 0, which makes sense. It's not moving. All right. Here's another example. Graph position versus time for the following motion dot diagram. So it looks like the spacing between each dot is increasing. And we said earlier in the example that the truck is accelerating. So it's speeding up in this case. All right, and if you want to draw that graph, this is what it would look like. So a couple of things to notice here. We can't draw a line of best fit for this graph because the data is not linear. We will look at, in one lab, a few labs actually, we will look at how to linearize data. Okay, so you can actually do that with this data and get some values, but we'll look at that when we get to a certain lab. All right, so notice that the slope is getting larger as time increases. And like we talked about earlier, slope is velocity. Slope of the graph is velocity. And since the slope is increasing, that means velocity is also increasing. All right, so how could we calculate velocity in this case? So that's a little bit more of a trick here. We could calculate either an average velocity or an instantaneous velocity. And so we'll take a minute and go ahead and do both of those. Okay, so we can calculate average velocity and we can calculate instantaneous velocity. So let's start with average velocity because that's pretty easy. So if you remember back from our definition of average velocity, we said that average velocity is equal to delta x over delta t, or just x2 minus x1 over t2 minus t1. So if we wanted to find the average velocity for the entire 6 seconds, we need to pick 2 points. The one at 6 seconds, use a different color so we can see that. So the one at 6 seconds, which is right here, and then the one that's at 0. And this is at point x equals 36 meter and time equals 6 seconds. And then the other one's at 0, 0. So that's going to be 36 meter over 6 seconds, which gives us 6 meter per second. Okay, we could, let's just say they wanted to know the average velocity for the first 3 seconds. So we would have done so this is 0 all the way to 6 seconds, and then this is 0 to 3. In this case, it would just be, now we're looking at this point right here, that's going to be equal to, it's kind of hard to tell here, but it's about at 9. So this is going to be 9 meter over 3 seconds, which gives us 3 meter per second. So you can see that the velocity over time is increasing. The average velocity is, and the instantaneous velocity. Okay, you don't have to go from 0 to some other time. You could go from, let's say we wanted to know average velocity between 2 and 4 seconds. You could use that time interval. So it doesn't really matter there. Okay, let's say we wanted to know the exact velocity at a point. So we just found the average velocity for the first 3 seconds is 3 meter per second. But what if we wanted to know the exact velocity at 3 seconds? So that's a little bit more difficult. Okay, I'm going to show you one way you could think about doing that. And one way you could think about doing that is you could pick 2 time intervals. Let's say we picked 2 and 4. All right, so I'm just going to draw some lines here. Let's say we picked between 2 and 4. If we found the average velocity for that time interval, that's going to be pretty close to what the exact velocity is at 3 seconds, right? So these 2 points right here would make up our delta x, and then this time interval would make up our delta t, that 2 seconds. So think about how could I make this even closer to the exact velocity at 3 seconds? Well, what you would do is you would decrease that time interval, right? So maybe instead of going from 2 to 4, maybe you would go from 2.5 to 3.5. And then if you wanted an even closer answer, maybe you would go 2.75 and 3.25. So the idea here is if you want a more exact answer to what the velocity would be at 3 seconds, then you would keep decreasing that time interval to as small as possible. Okay? And that's sort of going to lead us into how we use calculus to find instantaneous velocities. Okay, so we're not going to do that right now, but I am going to show you a trick that you could do to find the exact velocity at 3, or a really close estimate. So we know that velocity is slope. So we're really wanting to know what is the slope at this point. And so what we could do is draw a line that is tangent to that point. So if I draw a line tangent to that point, it's going to look maybe something like this. So a line tangent, maybe more like this. Okay, so a line that is tangent to that curve, it just touches that curve at that exact spot, 3 seconds, just one time. So maybe the line looks something like that. And now we've made up this line, and we could find the slope of this line here using the points on that red line. So let's go ahead and try that. So we're going to have to estimate here. So we'll pick at 2 seconds, and we'll pick at, just to kind of get a better average here, we'll pick at 4 seconds. And we want those data points to find our instantaneous velocity. All right, so basically, if you're asked to find exact velocity, but you're not given any kind of function, you're just given the graph like this, this is how you would find instantaneous velocity. All right, so we're going to use these 2 points here. Okay, so let's go ahead and write those down. We're estimating here. So this one at 4 seconds, the position we're going to guess is, it looks like it's a little bit over 14. So you could just guess, I don't know, we'll just say 14.2 meter. Okay, and then the one at 2 seconds, we're going to guess again. I would just say it's almost 3. So maybe we'll just say 2.9 meter. Again, we're just guessing there. Okay, so now to find the instantaneous velocity, so these two are average, and then this one here is instant. At least it's an approximation. It's probably not exact. So we're going to have velocity is equal to 14.2 meter minus 2.9 meter, and divide that by 4 seconds minus 2 seconds. So what is that going to give us? That's going to give us 11.3 over 2. And that's going to give us, let's see, like 5.6-ish. I don't know. Let's just say 5.6 meter per second. We'll just guess. All right, so 5.6 meter per second. And if we look, earlier we said the average velocity for the first 3 seconds was 3 meter per second, but the exact velocity at 3 seconds is more like 5.6 meter per second. So that's how you find instantaneous velocity if you're just given the graph but no function. Okay, later on we'll learn how to use calculus if given a function to find the instantaneous velocity. Okay, in this example we want to graph the position versus time for this diagram, and I went ahead and labeled the distance of each oil drop for you. So see if you can take a second and try to draw the position versus time graph for this. So we said earlier the object is slowing down. We can tell because the oil drops are getting closer and closer. And so the graph for that position versus time graph would look like this. So what you should notice here is that we can't draw a line of best fit. The graph isn't linear. Instead, we just draw a curve. So we can calculate average velocity by picking 2 points and finding the slope, just like we did in the example. And then we could calculate instantaneous velocity by finding the slope of the line tangent to the point that we're trying to find the instantaneous velocity at, let's say 3 or 4 seconds, or by using calculus. So if we're given position as a function of time, then we'll start using calculus. So notice that the slope is tending towards 0, and slope is velocity. So notice that that slope is constantly getting smaller and smaller until once you get closer to 6 seconds, it's almost, it's not very steep at all. So that means that the truck is slowing down and coming to rest. All right. So on this page, we're just going to summarize different types of graphs that we might see for position versus time. So the first graph, the object is at rest. The position doesn't change as time changes. The slope of the graph is 0, so velocity is 0. In the second graph, we have a linear position versus time graph. This indicates that the object is moving and it's moving at a constant rate, which means there's no acceleration. We're not speeding up or slowing down. The last one, same idea. We have a linear graph, which means that the velocity is not increasing or decreasing. It's constant, no acceleration. But in this case, the slope is steeper, so it's going faster than the second graph. All right, in the first graph on this page, the velocity is still constant. It's just moving in the opposite direction. We're moving in the negative x direction or negative y direction, whatever variable you're using for position. So negative slope indicates object is moving in the negative direction. All right, and then in the second one, we have an increasing slope, which indicates that the velocity is increasing, and acceleration is not 0 in this case. We're speeding up. And finally, in the last example, we have a slope that is constantly getting smaller and smaller as time goes on, and this indicates that we are slowing down and the object is eventually coming to rest.